Hi, everyone. Thanks so much for joining. We'll give it a few minutes for everyone to get online, and then we will get started. I always love all the messages coming in. Feel free to post not just hello, but where you're saying hi from. Okay, and we're going to get started. Similar to a few weeks ago when we had Jay speak, we are lucky to have Bryce, who is a quantum computing applications researcher at IBM. He's going to spend a few minutes talking about his journey into quantum computing, what he's currently doing, and any advice that he has for all of you. So, Bryce, I'll turn it over to you now.
Thanks. It's great to be talking to everybody. As Kira mentioned, I'm a quantum computing applications researcher at IBM. So I've been there just a little bit over a year. Before that, I was at the University of Texas at Austin, where I did an undergrad in a bachelor's in electrical and computer engineering. I didn't formally prepare like a speech for everybody, but I'm just going to monologue for a little bit about my path to where I'm at now and some thoughts that on what I would do differently if I were in one of y'all's shoes at this point, right? So I was very fortunate to know early on that I was interested in quantum computing. So about my sophomore year in high school, I was pretty sure that this is what I wanted to do, and I was trying to pursue it the best way that I could. So at the time, I thought that what made sense was that I would go pursue an undergraduate degree in electrical or computer engineering or computer science. Just get some computing foundation, and then go on to grad school and get a PhD in physics. And I thought that would give me the computing, it would give me the quantum, and it would kind of set me up with everything that I needed to do research in this field. And as you can tell, like I ended up not getting a PhD, and so I'll talk a little bit about why that is, at least at the current moment. But I had these like really rigid plans of what I thought I needed to do in order to get to this point. And my plans were actually totally shattered after my senior year of high school, right? I thought that in order to really be competitive, I would need to get into like an Ivy League college that had a really strong program in quantum mechanics and had professors that were doing research in quantum computing. And at the time when I started at UT Austin, they didn't have any of those resources for me, really. They had a physics department, but there wasn't really any quantum computing research happening, and that was kind of a low point for me personally, right? But what I did instead is I just found any kind of research that I could get a hold of, right? So I started participating in a nanotechnology research group, and then started to just study outside of my courses, right? So if they couldn't really teach me quantum computing, then I was going to try and teach it to myself, right? And that started by reading some books. Like Quantum Computing Since Democritus was actually the first book that I read, which was really helpful for me because even though I read through it, and at the very end, it's not like I understood quantum computing. I was still clueless, but it kind of told me more of the things that I didn't know, right? So it went from having unknown unknowns to known unknowns, which was a start, right? And from there, I could start to direct my own reading and kind of drill down on those things a little bit more, right? But as I continued through undergrad, right, a big thing that helped me personally was that I was trying to find a community of people around me that had similar interests, right? I was more or less the only person that I knew at the time that was interested in this, and I didn't really have any resources to help me, right? At the time, there weren't a lot of courses for undergrads. You could find lecture notes at the graduate level, and there was textbooks, but in terms of like educational resources to really get started, they were almost non-existent, right? So what I started doing was I started an organization at my university to teach people quantum computing as a way to force myself to learn it, right? So I promised freshmen coming in that I would teach them quantum computing, and I ended up soliciting some help from some graduate students to help me make sure that these courses that I was teaching were correct. And that was the way that I ended up being able to learn this, right? Is that, I knew that at the end of the day, my classes would take priority. So unless I really obligated myself to someone else to do this, then I knew it wouldn't get done. And, I think fortunately, a lot of you guys and girls are in a better position than I was, right? In the last 4 or 5 years, there's actually been a ton of progress being made in terms of resources and opportunities that are starting to crop up. This course being one of them. This is something that I would have been extremely grateful to have had offered to me at the time. And so I'm jealous of you all for that. But a big piece of it was that, at the time, the job that I currently have didn't really exist. And I knew that, right? I knew, and it especially didn't exist for people who didn't have PhDs, right? So I spent most of my college career really pigeonholing myself into a job that, as far as everybody could tell, did not exist at the time, which was a risky move, I will admit. Not that I would have been hungry if I didn't get this job. I'm sure I could have found something that would have been great. But I think, although I can't apply that advice to everybody, right? I do think that, if there's something that you're very passionate about, even if you can't really see the full path of how you're going to get to where you're going to go, being really passionate about something and working hard at it can take you a long way. So I would offer that encouragement to anybody that, just because you can't put all the pieces together and see exactly the steps that you need to take, don't stop letting up on these things, right? Something that is always, it's been meaningful to me, advice that I got when I was younger, that no matter what you do, you'll never be as good at it as the person who loves to do that thing, right? So why do anything if you don't love it, right? And I really took that to heart, and that was something that I carried with me through college, right? And so if I had to do things differently, right? If I was starting as a freshman in college right now, I think that my path would probably look a lot different, right? I think, for one, I think everybody who's participating in this course is probably off to a good start, right? You definitely knew, for everybody who's, less than a sophomore in college, I mean, you already knew more than I did at that time. So you're already ahead of me, right? So as long as you keep on it, you have a head start, and so that should be encouraging to everybody, right? But the other thing is definitely getting involved in projects, right? So half of it is having the passion and the patience to study this material. It's not simple material. It's famously difficult to wrap your head around, but I think it's worth it. So that's definitely a piece of it. The other half is networking, right? So it's a relatively small community, and just like I was saying earlier, the job that I currently have didn't exist, and it wasn't once it did exist, it wasn't usually offered to people in my position. So how do you bridge that gap between working on your own skills to make sure that you're qualified, and actually getting in the room with the people who can offer you the job that you want, right? And that really does come down to networking, right? And so even for those who may not ultimately pursue quantum computing, right? You may go down this road and then decide it's not for you. Find something that you're more interested in, that you care about more. That skill will take you far in any industry, right? So for me, what that looked like is a couple years into my undergrad degree, my school hired a professor for that studied quantum computing, and so I was very lucky for that. And so I went and asked if I could be a fly on the wall in his meetings. Essentially, I asked, first of all, if his graduate students would help me with that organization to teach freshmen, and I asked if I could just sit in on his meetings, right? So I wouldn't go and bother everybody or derail the conversation with questions. I would just sit in the back of the room and take notes, right? And slowly learn from these people, and they would talk about things that I had no idea about, and I would write them down and then go look them up later. And by being a fly on the wall in those meetings, I started to meet different people that would come by to come come, visit the group or do other things like that. And those connections ended up being extremely valuable to me, right? That's ultimately how I ended up meeting some people that worked at IBM. And, those connections eventually led to this job, right? They also, led to the internship that I got, right? But that's not to say that if your university doesn't have a group like that, that there's nothing you can do, right? So, there's a ton of resources online now as well, right? Like I think, the one that I'm biased toward is there's a Slack channel for QxQ, right? And there's a ton of engagement that happens in that Slack channel. People like me and other people I work with at IBM are constantly answering questions. And by being engaged in projects like that, people get invited to these QxQ camps and they get to meet, actual researchers and network with each other, right? So even outside of IBM, right, a lot of the people who may come to these hackathons that we throw may go other places in the community, and so the connections that the participants make are extremely valuable, right? The first QxQ camp was actually how I got my job. I got invited to the first QxQ camp and ended up meeting the right people while I was there, and my project did well, right? So so I think one of the benefits, again, I know this is kind of a winding path through all of this. One of the benefits that I think, all of you have that I didn't have is the ability to kind of participate in a community like this, right? You can start working on projects right now. You can, start tinkering with, Qiskit or whatever other tools you have access to, and meet people in the community that are excited to work on it with you, right? I mean, it can be hard to be the only one who's interested in this thing that, as far as you can see, right? You might be the only one in your family that knows how to code, and that's a great thing. And it's like, I'm sure they're very proud of you, but it can be hard to say like, oh, like I want to do this crazier kind of coding called quantum, and you're like that's great, and but unless you have people around you, it can be a lonely thing at times. So I would encourage everybody to connect, whether that be over a Slack channel or over Stack Exchange. Start working on these projects, start tinkering around with these things. You can start building up intuitions for how these things work in practice, and those are very valuable skills, right? So maybe I should talk a little bit about what I do at IBM, and as a way to kind of connect the dots here, right? So quantum computing is a very diverse field, right? It's really at the intersection of at least 3 different, full research fields, right? You have mathematics, physics, and computer science, right? And people come at it from lots of different directions. I personally consider myself an engineer, right? So I'm fascinated by the theory and the computer science of it, but what I do in practice is more like engineering type questions, right? So, okay, you have an algorithm and you can prove that asymptotically, or, in some limit, it outperforms, but what does that really mean, right? If I go to try and implement it, how well will it perform, right? What are the details that I need to really think about to make this work in practice for a real problem that people actually will benefit from? And that's a lot of what I do at IBM, right? So we have researchers who work on the theory, which is extremely important. We have researchers who work on the hardware. My team does research with our client partners, right? So these companies will join, it's called the IBM Quantum Network. And that means that they get to interact with our researchers and use our hardware, and there's lots of benefits they gain. One of the highest forms of engagement of working with us is we do a research project together. And so I work with different clients who their company is interested in what can quantum really do for us, and where will it impact our business. And so me and a couple people from IBM will get together with a few researchers from whichever company. Maybe that's Goldman Sachs, or maybe it's Samsung, or JP Morgan, or there's lots of different companies, and they will show us the problems that they're working on that are really hard for them to solve, and we will work together on trying to figure out which ones might be solvable on a quantum computer, and which ones could we start building solutions for right now. So a lot of what I do is trying to bridge that gap between what we know quantum computing can do semi-abstractly, and what would it take to actually run it, right? Like how big of a computer will we need, really? Like how low do we need the error rates, and how much performance can we squeeze out of the limited hardware that we have right now, right? And so to that end, I see these potential projects that I'm encouraging everyone to work on as being extremely valuable, right? Like being able to tinker around with these tools and understand them deeply and understand, you know, the limitations of them and where the trouble is. You know, all of those things are super important, right? Like those are the kinds of experiences that can lead to, you know, practical insights about where real progress can be made, right? Like where, you know, by using these tools and you know, you might run into certain frustrations of, man, I really wish that you could just do this, right? I really wish it had, you know, the ability to just cleanly do this, and that might be the thing that you do, right? And until you have really, you know, played around with it, you know, you'll never know that, right? And so so that's one thing. I think I'm over time, but again, I think the last thing I'll leave everyone with is, you know, definitely maintain your resolve, right? If this is something you're passionate about, you know, keep at it, even if you don't really see how it, you know, it will play out, and seek out mentors and get involved in the community. And then with that, I think I'll hand it back over to Kira, because I've gone over time. Thanks, everyone.
Thanks so much, Bryce. And just before you sign off, could you just post in the chat to all the attendees what the name of the book was? We are just getting a lot of questions for students who would like to read it. That'd be awesome. So before we officially get started with the lecture, again, just want to thank you, Bryce, so much for taking the time to talk with all of us. We do have a pre-course technical assessment that we would need you all to take. It's a completion grade. It counts nothing towards your final grade except the fact that you completed it. It's in Canvas. And Gabby, if you can just explain, want to explain how students will can access it, that would be amazing. But the bottom line is, we don't expect you to know this knowledge. It's a way for us to make sure that as the course goes on, you are aware of you know, what's being covered, and we can, at the end of the course, we'll have you all take this again and really see what you were able to learn. So if you don't know the answers to things, you can just actually put, you know, I don't know, don't guess on them. That's not helpful. It's more helpful if you don't know the answers, to write, I don't know. And then at the end of the course, when you retake this survey, if you know the answer, we'll be able to say, okay, we were able to teach this effectively, and we can keep on doing this. Or if a group of people don't know the answer to something still, then we realize we need to go back and make adjustments to the course. Yes, Gabby, I'll let you explain where it is.
Yeah, I'll share my screen real fast so you all can see where to find it. My screen looks a little bit different than yours, but if you go on the side here and click on quizzes, it'll show up as one of the, as soon as it loads. Maybe it won't.
Gabby, what's it called, just for everyone's knowledge in case you can't open it, but it is in quizzes?
Yeah, it's called Semester 1 Technical Assessment, and it's ungraded. And Kara, if you want to explain a little bit more.
Yeah. Again, it's just a completion grade. We're going to give you about 10 minutes to take it. Most of the material you should not know, and that is completely normal. Again, it's not about getting 100%. Please don't look up any answers. Simply, the goal is, and anyone that's watching the recording of this will need to take this as well. We are going to require you to complete it in one shot. So you can't go back and you can't submit multiple times. Again, this is just a way for us to assess where students are now, and then at the end of the course, again, where what you've learned. This is also a really critical way as a nonprofit for us to secure funding, to make sure that our courses are effective and that you all are learning, you know, the material that we set out for you to learn. So again, the larger jump in from what you don't know to what you do know is incredibly important. So we'll give you the next 10 minutes or so to take the quiz. We'll also open up a poll so you can mark when you're done, and we'll move forward when most individuals are done. Fran, if you just want to start sharing your screen though, just so we have a background for the welcome.
Yeah, and just to, I guess, add to what Kira just said, I helped her write this quiz, and I will add that it is very challenging. Once you guys all master quantum computing, you should be able to get through it no problem, but coming in with little background, it definitely will be challenging. So definitely, if you don't see a solution right away, don't spend too much time thinking about it, and just move on, because these should be questions you can answer rather quickly if you are comfortable with the material.
And I'm being notified that Discord is down, or not Discord, sorry, Canvas is down for some people. Gabby, could you just open up a poll really quickly to see who's been able to access the quiz and who hasn't? If you haven't, you can take it afterwards or before. Okay, many are unable to access it. So we may have to wait and have you take it afterwards. But we'll give it a few minutes for those that have been able to complete it. But then we will move on probably in the next few minutes if people aren't able to access it, and we'll just ask you to take it afterwards. Sorry for Canvas being down. That's outside of our control. But yeah, later on today, if you can take it, then that would be awesome. And again, if you are able to take it, make sure you're marking I don't know. If you don't know the answer, don't guess on them. We'll just give it another few minutes for those that are able to access Canvas. But again, we will get started soon. And if you're unable to access it, don't worry. The assessment will be available all week. We just do, again, as Gabby mentioned, like, do not guess, just mark I don't know if you don't know the answers. It shouldn't take you very long to do, because again, you haven't been taught most of the material. So you shouldn't know the answers to it. I also have already taken the assessment, and it did not take me long. So don't worry or feel overwhelmed. By the end of this course, you'll be able to answer the questions that are on there. Okay, and with that said, let's get started, and I'll turn it over to Fran to keep us going.
All right, thanks, Kira. It's great to be giving my first technical lecture today. So I guess you guys have had 2 lectures with Amir now. And for the rest of the semester, for the most part, as we're going through a lot of the math, I will be giving the lectures. So today's lecture is going to be focused on intro to vectors and complex numbers. And I just wanted to start off today's class by sort of motivating why we are actually spending so much time going through math in a quantum computing course. And before I even go into that, I just want to start off by saying all of you, I'm sure, are coming from very different backgrounds. Some of you have probably taken calculus, whereas others of you might have just finished taking algebra, geometry. And so the point of these next few weeks will be to try and get you all on the same footing, the same level, so that when we start getting into the actual quantum computing, quantum information, you can really start, make sure you're focusing on the physics and the quantum computing topics rather than worrying about the math that we'll need to really understand those topics. I personally felt very strongly about putting a large emphasis on math in this course because actually, for myself personally, when I was at MIT, the first time I tried to take quantum mechanics, I hadn't taken a proper probability course, and I was simultaneously taking my first linear algebra course. And I just felt extremely overwhelmed. There's a lot of really challenging concepts you have to wrap your mind around and a lot of conceptual difficulties. So if you're simultaneously having to worry about like the simple math techniques and things like that, it can quickly get very overwhelming. And so for myself personally, I did really terribly the first time I tried to take quantum mechanics because I just didn't have a math background. I had to drop the class, but then I finished my linear algebra class. I took a very good probability course, and by the second time I went to retake quantum mechanics, I felt much more confident in my abilities and was really able to rock all of that quantum mechanics knowledge. So that was just my quick blurb for why you should all want to follow the math. For those of you coming from more advanced math backgrounds, you should just look at these next few weeks as a review and really making sure you are solid in all of those foundations that will be necessary for quantum computing. I just want to put a general disclaimer though, that even though we're calling this sort of intro to linear algebra, intro to probability, when you do get into a college setting, it is very important that you actually go and take a proper linear algebra and a proper probability course. This is just enough to get you through the class and started in the field. But if you really want to branch out, do cool research, work on awesome projects, the more background you can get, the better. And with that, here's just like a fun little slide I made, again, sort of motivating the math. The first point is that the math is a necessary foundation and tool set for the quantum to come. And even irrespective of whether you end up going into quantum computing, linear algebra, probability, complex numbers, the core of what we'll be focusing on these next few weeks, is useful for every field of STEM. I've done work in electrical engineering, in physics, math, and computer science, and even if you end up in biology, chemistry, all of these fields use these basic tools and build off of them. So having a strong foundation will really prepare you in the future to excel in whatever field you go. And the last key point that I want to emphasize is that this math is very hard, and we're going to be throwing it at you very quickly and a lot of it all at once. So if you don't understand everything the first time, that is totally okay. You're going to need to do a lot of practice in order to really master these topics. So throughout the lecture, I'm actually going to be having a bunch of what I call quantum quiz times, where I will show you problems directly related to concepts I've just explained, so you can start to get some practice. I know Akshay has prepared a bunch of really great recitation or lab content for you guys to work through, and then really make sure you're doing all of the homework assignments. Our head of homework, Brian, has also incorporated a bunch of optional practice. So if you feel like the required problems, you still want more practice, make sure you're doing those as well. And then I guess lastly, the final sort of fun point that I wanted to make is that if you master the math, you can also understand all the math memes, which is, of course, a really great reason to learn a lot of math. All right, and then sort of to conclude my math motivation, I actually wanted to finish off with a quote from Professor Scott Aronson's book, Quantum Computing Since Democritus, that Bryce was talking about and actually shared in the chat, that sort of really hits home, I think, why the math that we're going to be learning is so cool, so awesome, and so relevant to quantum computing. So just to read through this really amazing quote from the preface of his book, he says that quantum mechanics is a beautiful generalization of the laws of probability, probability being one of the concepts we'll be covering, a generalization based on the 2 norm rather than 1 norm, and on complex numbers rather than non-negative real numbers. It can be studied completely separately from its applications to physics, and indeed doing so provides a good starting point for learning the physical applications later on. This generalized probability theory leads naturally to a new model of computation, the quantum computing model, that challenges ideas about computation once considered a priori, and that theoretical computer science might have been driven to invent for their own purposes, even if there were no relation to physics. In short, while quantum mechanics was invented a century ago to solve technical problems in physics, today it can be fruitfully explained from an extremely different perspective, as part of the history of ideas in math, logic, computation, and philosophy about the limits of the knowable. So I think that's a really cool quote. And with that, we will start moving on to the actual technical content. So today's lecture is going to be jam-packed with a lot of fun ideas. We're going to start off by going through vectors and what exactly that means, and then we'll transition into discussion of complex numbers. And these two topics are actually very related, so hopefully this relationship will become apparent to you as we move into the second part of the lecture. All right. So with that, let's start off with our intro to vectors. And just as a note, I really love memes, so you'll probably see plenty of memes sprinkled throughout the slideshow. In this case, you just got vectored. Here's a little vector from Despicable Me, for any of you who have seen that movie. It's one of my favorites. So we'll start off today's lecture by first diving into what a vector is. And to do so, we're going to relate it to a topic I'm sure all of you are familiar with, which is scalars. Even if you're not familiar with the term scalar itself, a scalar is a quantity that has only a magnitude but no direction. And it's what we typically think of when we think of numbers. It's usually written in this form, A in R. This is like a math notation. If it seems a bit like a bit of jargon to you, that's no problem. Essentially, it just means like it's in the set of real numbers. And there's a few examples that I've listed out in physics that I'm sure you're all familiar with. We have distance, speed, time, and mass. A vector, on the other hand, is a quantity that has both magnitude and direction. So it's, instead of being a single number, it's described by a list of numbers or scalars when we express it in Cartesian form versus or radius and angle, which is the polar form. So in the high school review that you guys were all doing this week, you should have had a good review of Cartesian and polar form. And when you plot points on these planes, you can similarly think of them as vectors, and we'll be getting into that in a few minutes. The notation for this is a bit different. The main way in which we sort of distinguish vectors is by drawing this little hat on top of them. And instead of being in the set of real numbers, it's in the set of real numbers to the power of n, where n denotes the dimension of our vector. Again, this is pretty mathy. We'll be breaking everything down in the next few slides. So some examples in physics, in contrast with scalars, are displacement, velocity, acceleration, and weight. All right, And so in this next slide, I just wanted to show you all some different examples of scalars that you might be familiar with. So we have a set of 30 M&Ms. That's very quantifiable, can count 30 M&Ms. There's no sense of direction. The fire is 1,000 degrees Celsius, or my USB drive can hold a terabyte worth of data. For vectors, on the other hand, we have these examples. So the first example is you have a drone or a UAV that's flying upwards at 10 meters per second. So the drone has a speed, which is 10 meters per second, but it also has a direction in that it's flying in the upward direction. The second example is just me having a bit of fun with the Newtonian laws of physics, if you're familiar. Basically, every force has an equal and opposite force. So we're saying that Isaac Newton is slapping the car with a force of 20 newtons at negative 20 degrees. So this is the magnitude and this is the direction again. But because the force is equal and opposite, the car is slapping him back with a force of negative 20 newtons at negative 20 degrees. And so for our final example, we won't be getting into this right now, but it's sort of a preview of what's to come later on. It turns out that quantum states are actually represented as Bloch spheres in this space that we call the Bloch sphere. But essentially, you can see here, this actually is what a state looks like in the case of a single qubit. And throughout the course, we'll sort of be building up the intuition so that in second semester, you can see exactly why this is the case. And with that, I wanted to start off our first quantum quiz. So note that these quizzes are going to be a bit tricky. They're meant to really sort of test if you've understood fully what I've been talking about. So if you get it wrong, no problem, but I'll give you a few minutes. The goal here is I'll give you just a minute. The goal is to determine whether each of the following is a scalar or a vector. And you have to think a bit carefully. All right, since this isn't too involved of a problem, I'll go and show the solutions really quickly. But again, I'd encourage you all to come back to the slides afterwards and sort of re-quiz yourself with these questions and check the solutions again if you have any questions. So in this case, our first example is just the fish is swimming at 1 meters per second, but we didn't specify any notion of direction. So in this case, it is a scalar. In the second case, the boy is kicking the soccer ball at a 40-degree angle with a force of 12 newtons. So this has both a direction and magnitude, so it's a vector. In the third example, we're saying that the piano has a mass of 160 kilograms. Since mass does not have like a notion of direction, this is actually just a scalar. Oh, this should say the polar bear. But anyways, the polar bear example is actually a vector because when we are considering the concept of weight, we're also considering the fact that gravity points inwards towards the center of the earth. And so there is a sense of downward direction. These last two were a bit tricky, and if you don't have as much physics background, might not be as clear. But if you got the first two, you'll be in good shape. All right, so now let's actually start thinking about what exactly a vector is and how we represent it. And to do so, I want to start off by just writing out an example of a vector that you might have actually already seen in a math class, which is typically referred to as array. So let's say we have array, which we call AB. So this is going from the point A equals 2, 2 to the point B equals, let's say 6, 7. So now if we go and we plot this in our Cartesian coordinates, we'll see that the point A right here, 2, 2, I'll denote that as green, and B will be in red. It's at 6, 6, 7. So this ray is essentially, it has an initial point A and a terminal point B, and we call the ray or the vector connecting these 2 points to be AB. Now, typically what happens when we're working with vectors is we don't actually care about where it's starting off. We just sort of want to quantify it in terms of its terminal point. So in typical vector notation, what we'll end up doing is we'll move this initial point A to be at 0, and then we have to apply a similar transformation to B. So we'll get this vector that goes from A to B, and let's say, since this is now a proper vector, we'll call it VAB, VAB. And so it starts at the point 0, 0, and finishes at the point 4, 5. So this here is a vector quantified by 0.45, and in general, when we write out vectors, we determine them solely by their terminal point. So if I were to give you guys another example, let's create a vector W, which let's say goes to the point 1, 8. This top component here corresponds to the X component. This bottom part here corresponds to the Y component of W. And so our vector ends up looking like this. So this is just an example of how you represent a vector. When you guys were practicing with Cartesian form, I'm sure you did practice where you were just sort of writing out points. In the case of a vector, it's literally just a point, but we're assuming there's a connection between the origin and the end, which gives it a notion of magnitude and direction that we'll be exploring in the next few slides. So, and again, this equation here shows the general notation for a two-dimensional vector. Okay, so here I just wanted to have a quick example about writing out vector representation for the following 3 vectors. So I'll give you guys like 15 seconds, just go through on a sheet of paper and jot out what the vector form for each of these 3 vectors. And all right, so hopefully this wasn't too hard. Basically, to break it down really quick, the vector A, we can get its x component just by going down. We see that the x component is at 2. This gives us the 2 here. And then if we look at the y component, we're at 7, which gives us the 7 here. And you can use a similar procedure to write out the vector representation for all of the 3 vectors. We're a bit pressed for time, so I'm going through these examples fairly quickly. Here's just an example for you to get some practice plotting vectors on a Cartesian plane. So I wrote out the vectors, just take a few seconds, draw out a Cartesian plane and try plotting these out.
And just for everyone's knowledge, when it's, as Fran mentioned, for the quantum quiz time, you're not being graded anywhere. You don't need to submit the problems anywhere. It's simply practice time. So you just practice, and then Fran will go over the answers. And Fran, don't worry about the time. I would you can take it slow, and then if we need to go over, the recordings can be available for anyone that needs to go.
Okay, sounds good. Yeah, these are some concepts that just require a bit of practice, but it's mostly notation still at this point. So hopefully you guys are all feeling comfortable. And yeah, Kira, if you feel like I'm not giving enough time for people to answer questions, just let me know before I start going through solutions. But hopefully you all had enough time to plot these out, and we'll quickly go through the solutions. So this first vector A, we see that it has an x component of 1 and a y component of 0. So it's just plotted here along the x-axis and has a length of 1. B, on the other hand, has no x component, but has a dimension of 5 in the y component. So it looks like this. And then C has an x component of 3 and a y component of 4. So it's plotted like that. All right. And so with that, we'll go back to the idea of vectors having a representation in both the Cartesian coordinate plane and the polar coordinate plane. So let's quickly start with an example. Let's imagine that we have the vector v equals 5, 5. So plotting that in the Cartesian coordinate plane, we go to x, we have a component 5, we go to y, we also have a component 5. So our vector just looks like this. That being said, though, we can quantify a vector not only by its x and y components, but also by its magnitude and direction, which is quantified in terms of a radius, which we typically refer to as r, and an angle, which we typically refer to as theta. So in this case, the vector 5, 5, we can calculate it out, but it'll have an angle of theta equals pi over 4. So if this is our x-axis here, our angle theta looks like that. And then our radius is 5. So we go 1, 2, 3, 4, 5. So it actually only comes out to right around here. And so we see that this vector in polar coordinates can be represented as well by a vector of radius 5, or theta equals pi over 4, and this is radians. This is also equal to 45 degrees. And so over the course of the next few slides, we'll be figuring out how exactly you can, in this Cartesian coordinate form, determine what the radius and angle theta are mathematically, given the x and y components. But I just wanted to show an example. And again, you guys should have had some practice with Cartesian and polar form already in lab. So hopefully this is not super unfamiliar. So there's a fairly simple equation that we can use to calculate out vector magnitude, which looks as follows. And it's important to keep in mind the notation for vector magnitude looks like this. We just put the 2 bars around. And the vector magnitude is essentially just equivalent to the square root of the x component plus the y component, both of those squared. So let's work through an example really quickly of this. So let's say that we have the vector v equals 6, 4. We'll draw that out really quick. So if we want to calculate the magnitude of this vector, we go v equals square root of 6 squared plus 4 squared. And then you don't actually have to calculate it out. I worked it out beforehand, but this is 36 plus 16, which is then equal to square root of 52, which is approximately 7.21. And sort of a good check that you should always use when you're calculating out magnitude can actually come from geometry, your Pythagorean theorem, right? You have sort of the two legs of your triangle, right? One which has a length of 6 and one which has a length of 4. And the magnitude, it corresponds to the length of the vector. So the vector has magnitude and direction, length and direction. And so from Pythagorean theorem, right, we know that the hypotenuse is always going to be greater than either of the legs. And here we see that as well. 7.21 is greater than 6 or 4. That's just a quick check you can use. So that was how we find out the magnitude or length of a vector, but similarly, we can also calculate a vector's direction. And we'll again use the same example of the vector 6, 4. I can draw a line. And so just as we did in the last example, actually, we again sort of think about it, right, as a right triangle. It has the x component 6, the y component 4. And so for those of you who are just doing the trig review, given that you have the two legs of a right triangle, how can you figure out the angle? Well, you can use SOHCAHTOA, right? That's the important rule to remember, right? And so we have the opposite and the adjacent, so that gives us TOA, opposite over adjacent, so we should use the tangent. And so we know that tangent of theta is equal to y over x, which in our case is 4 over 6. So that means that our angle theta is the inverse tangent of 4 over 6 in this particular case, and that's sort of the rationale as to why the direction of our vector has this specific formula. If you're trying to solve tan minus 1 is the same thing as arc tan if you're using a calculator to calculate it out. And I worked this out beforehand to be approximately 0.6 radians, which is equal to roughly 34 degrees. And if we look back at our vector, right, the 45 degree angle would be sort of going from the points 0 to 6, 6 or to 4, 4. This would be 45 degrees. So it looks roughly reasonable, right, that this is around 34 degrees. So I personally am a big fan of just doing quick sanity checks to make sure I didn't do any sort of miscalculations when I do any involved calculations like this. And with that, I wanted to give you guys time to go through yourself and try and calculate out the vector magnitude and direction. You don't have to actually bust out a calculator and calculate the specific values. If you just write it out in the equation form, that's fine. All right. Hopefully you guys had some time to work it out. I'll quickly just show the solutions that I did beforehand. So in this case, to calculate the magnitude, remember it's the square of the components of the vectors summed, and then take the square root of that. So you just get 5 squared plus 5 squared, square root, and this gives you square root of 50. For the direction in this case, since the components have the same magnitude, this is actually a direction that we can calculate mentally if we've gotten a bit of practice with the unit circle. So this is just arctan of 1, which gives an angle of 45 degrees. All right. And with that, I just wanted to move to a final sort of conceptual slide about direction and magnitude. So essentially, in this first figure here, I really wanted to emphasize that all vectors have the same magnitude, but different direction. And in this second slide here, or in the second figure over here, all of the vectors have the same direction, but they have different magnitude. And it's good if you, in looking at vectors, can spot like how the directions and magnitudes relate to one another. In the next lecture, we'll actually be working on, we'll learn a math tool that you can use to actually quantify how similar two vectors are in terms of both their directionality and magnitude, which is super cool. But for now, it's important that you just really rock the idea that a vector has a magnitude and a direction, and can distinguish between the two. And with that, we're going to start getting to move to all of the fun sort of algebraic properties of vectors. The first property.
Can't hear you. Ooh.
Sorry,
Fran,
I heard a weird beeping. Can you still hear me?
now we can hear you.
Oh, okay. My bad. Okay, so now we're going through the notion of vector addition. And this is fairly simple. The idea here is if you have a two-dimensional vector, you essentially only add together similar components. So let's say we define the vector A equals 3, 4, and the second vector B equals 5, 2. If we want to take the vector addition of these two vectors, A plus B, we take the two x components, 3 plus 5 and 4 plus 2, and that will give us, right, 8, 6. And one of the cool things about vector addition is that it actually has a really nice geometric interpretation. So let's start off by plotting the vector A. The vector A is 3, 4. And let's also plot the vector B, but let's plot it with the initial point connected to the terminal point of A. So we're starting B from here. And then we add 5, so that takes us to 8, and we add 2, takes us to 6. And we end up seeing, right, that, so here we have A plus B. This is A, this is B. And simply by plotting here the vector 3, 4, so here 3, 4, and then the vector here 5, 2, when we connected them start to finish, we actually got this vector a plus b, which we double checked has an x component of 8 and a y component of 6. So geometrically, you can interpret vector addition like this. One sort of neat thing to note about vector addition is it is commutative. So to quickly sort of work through an example of that, let's say we now define the vector. Actually, I'll color code this, make it a bit easier to follow. So let's say we have the vector a equals 1, 2, and the vector b equals 5, 7, for example. So let's start off by plotting each of these. So 1, 2, and then if we go here, we start off by plotting 5, 7. All right, so we have the two vectors, and now let's start off by trying to first do a plus b, right? That gives us 1 plus 5, 2 plus 7, so that's equal to 6, 9. Now let's double check then. If we put the vector b after the vector a, we do in fact get 6, 9. So if we take 1, we add 5 to it, that takes us to 6. If we take 2, we add 7 to it, that takes us to 9. Connect those. Then our resultant vector, a plus b, in fact, it does have components 6 and 9. And so sort of similarly with the second vector, in the second plot, if we instead do b plus a, we get 5 plus 1, 7 plus 2. But because order doesn't matter in addition, right, we still get 6, 9. And this is in fact reflected in our second plot. So we'll add 1 and 2. Make this our second one, and we get the resultant vector 6, 9, which is just a plus b. So it's very cool. Independent of the order that you add your vectors, you'll always get the same result. And so now we'll be going through the process of vector scalar multiplication. Sorry, this is just sort of a lot of equations and working through problems. This is all sort of just build up, and these are very important tools to know later on. So vector scalar multiplication is pretty intuitive. We have some scalar c that we want to multiply by the vector w. So what do? We just multiply c by both of the components in w. So let's say that c is equal to 2. W is, for example, equal to, I don't know, 3, 2. Then c times w is equal to 2 times 3, 2 times 2. So that gives us 6 and 4. All right, so if we go and we plot that, let's start by plotting w. So w is 3, 2. Now if we plot out c, we go to 6, 4. And essentially what this scalar multiplication has done is it's preserved the direction of the vector. All it's done is changed its length. So we've multiplied the length of the vector by 3. And so on this next slide here, I just wanted to show you for sort of different examples of what our constant c is, what effect that will have on our vector. So let me quickly just start off by saying, imagine that we have the vector w equals 1, 2. So let's imagine here that we're multiplying by a constant a, where a is equal to -1. Here we'll multiply by a constant b, which is equal to 1/2. C will multiply by just a factor of 1, and here D will multiply by a factor of 2. So try and think about it, but we'll also plot it out. So let's just start off by the case in which we're multiplying by a factor of 1. Essentially, this will just be 1 times 1, 1 times 2, and that'll give us 1, 2, the same exact vector. So here is our vector W. Now, in the case that we multiply by -1, what do you think will happen? Well, if we multiply by -1, we'll essentially get that both the x and y component will actually flip and become negative. So all this will do is it'll actually just flip our vector about the origin. So it'll be anti-parallel to our original vector. If we multiply by a factor of 1/2, we'll get the vector 1/2, 1. So that's just scaling it down to be half the length. And if we multiply by 2, we'll get the vector 2, 4. So it'll be a vector that's actually twice the length of our original vector W. And so in general, with constants, or with vector scalar multiplication, I think the key sort of thing to note is that the vector will always remain parallel, meaning in the same direction as it originally was. It'll just be scaled. And if the multiplicative constant is negative, the vector will actually flip orientation and become anti-parallel. So now I just wanted to give you guys all a mini quantum quiz where you'll just go through some practice adding vectors and also performing constant scalar vector multiplication. And if you can, write out the solution both algebraically, so write out both the vector notation and also think about how the resultant vector would look in the Cartesian coordinate plane. All right. Hopefully that was good time for you to think about it. So here I'm going to show the results really quickly. So in the solution for 1, we can see that the resultant vector n has components 8 and 8 from adding 7 and 1 and 2 and 6. And I also geometrically illustrated the fact that regardless of the order you add the vectors in, doesn't matter, you always get that same resultant vector. And for problem 2, we multiplied by a scaling coefficient of 1/2, which should essentially just half the length of the vector, as we see in figure number 2, where we went from a vector with components 8 and 4 down to a vector with components 4 and 2. All right, and so as we start concluding our discussion of vectors, this is just a very introductory discussion on vectors. I wanted to start sort of hinting at some more complex notions about vectors that we'll actually be exploring in the next lecture. And this is the notion of vector decomposition. So in the beginning, I sort of talked about a vector as kind of being like an array that you could translate so that it starts from the origin. In mathematics, there's very specific way in which people very frequently like to think of vectors, because it's a very useful representation, which involves vector decomposition. So we're just going to go over this from a high level, but let's start by defining the vectors x hat and y hat. And essentially, actually, I will use a different color. So the vector x hat just has a magnitude 1 and is pointed along the x-axis, whereas y hat has a magnitude 1 and is pointed along the y-axis. These vectors, it turns out, are orthogonal to each other, and we'll be exploring what exactly orthogonality means in the next lecture. But sort of the key thing to note here is that it turns out that any vector can be represented as a linear combination of these two vectors. So this will be sort of applying the ideas of vector scalar multiplication and vector addition that we discussed. So let's say we define some arbitrary vector, w, for example, is equal to 5, 4. One way that we can write that out, right, is we can say that that is 5 times 1, 0, plus 4 times 0, 1. And what exactly does that correspond to? Well, that corresponds to 5 times our vector x hat plus 4 times our vector y hat. And we can actually see this graphically. So if we take on our Cartesian coordinate plane, extend our x component out to be 5 and our y component to be 4, we get the vector w. And so this was an example for a specific vector w. In general, if we have some vector v, which has components vx and vy, we'll say that this is equal to vx times x hat plus vy times y hat. And so while this doesn't seem very complicated, assuming that you were able to follow the discussion on vector addition and vector scalar multiplication, this is actually a really powerful idea in linear algebra. It introduces us to the notions of linear combination, and it turns out that x hat and y hat are called basis vectors, which we can use to define any vector in the two-dimensional real plane. So very neat. Linear algebra is very cool, and we'll be getting to explore some more advanced topics in a bit. So I just wanted to conclude today's discussion on vectors by quickly going over the notion of vector generalization. So in this lecture so far, we've primarily talked about scalars and 2D vectors. And so as I showed on the first slide, scalars take the form of a element of real. And some examples of that would be like 1, 4, 7, 91, 1024, whatever numbers you like. Two-dimensional vectors, we said were element R2, again, noting this 2 here. So in the case of scalars, you could think of this as being essentially like a one-dimensional vector. And some examples of this are just like 5, 4, 3, 2, -1, -5, etc. And we represented these 2D vectors on a Cartesian coordinate plane, and they look something like this. And I only really referred to 2D vectors in this lecture for the sake of simplicity, but it turns out that you can actually have vectors with any numbers of dimensions. So if we generalize this a bit, let's say we have 3D vectors and call them W. Those would be element of real to the power of 3. So here 3 is our indicator that it's three-dimensional. And an example of this would be, for example, 1, 2, 3, 4, -2, 9, for example. And 3 dimensions are still fairly okay for us to visualize. So if we were going to plot the vector 1, 2, 3, this here is what a three-dimensional coordinate plane looks like. You just start at the origin, you move out 1 along the x direction, you move out 2 along the y direction, and you move 3 along the z direction. And now is kind of when I have to put my art skills to use a bit. So let's see, you get something that looks like that. And so that's an example of a three-dimensional vector, but it turns out we can keep increasing the number of vectors. So we could go to a 4D vector. Let's say Z R4. An example of that would be 1, 2, 3, 4. The problem is though, once you get past 3 dimensions, it becomes really hard to visualize a 4th dimension. Often that's like illustrated via time or something. So we actually don't really use vectors as much in these higher dimensions in the visual sense, but we're still able to apply the same linear algebra concepts like vector addition, vector constant, or vector scalar multiplication that we've already seen. And it'll all still hold very nicely. So I just wanted to wrap up this slide by writing out what an ND vector would be. So we'll just call that Q. It would be R to the power of N, and it would be a vector that has components Q1, Q2, all the way through Qn. And so with that, I wanted to sort of conclude our discussion on vectors for today by showing a review of all of the topics that I presented today, but actually in their most general form. So as we just discussed, if you have a n-dimensional vector, this can be represented as in our standard vector notation. It's just that instead of being a list of 2 numbers, instead it has n numbers in it, but everything else is the same. So for vector addition, what does that mean? Well, instead of just adding our x components and y components, for each of our n dimensions, we'll go through and add the components in those dimensions. For vector scalar multiplication, it also generalizes pretty nicely. We just multiply each of the n different components by the scalar. And then finally, for vector magnitude, instead of our vector length being defined just by the sum of the squares of the x and y components, it's the sum of the squares of all n components. So with that, I think that'll wrap up our discussion on vectors for today. I think we should probably take a quick, maybe 5 to 10 minute break before we start diving into complex numbers.
Let's take a 10-minute break. So if everyone will post in the chat when everyone needs to be back, but feel free to take a 10-minute break. And we know we've just gone through a lot of math, so relax and decompress and be back in 10 minutes.
Yeah, complex numbers should be a bit more fun and applied. So stay tuned. All right. It's 2:29, so I think I'll start again. Kira, is that all right?
Yes, go right ahead, Fran.
Okay, sweet. So over the course of the break, our amazing head TA Akshay compiled a list of some of the most commonly asked and also some of the best questions from all of you guys. So thanks for asking those. And before we dive into complex numbers, I just wanted to spend some time going through those questions. So I wrote down a quick list of all of them. So the first question we got is a one-dimensional vector a scalar? In like really advanced mathematics, there are some nuances to this, but for our intents and purposes, yes, you can think of a one-dimensional vector as a scalar. It only has a single component, which is the vector magnitude. There's no notion of direction, and sort of as I indicated during the lecture, we write scalars like this, basically, which is just implying that it has a single component. Some of you were asking about this notion of L1, L2 norm, which was referred to in Scott Aronson's quote from Quantum Computing Since Democritus. We will be discussing the notion of norm. It's actually just another way of naming magnitude a bit more in the next section. We won't necessarily be going into the specifics of L1 versus L2. Those are just different ways of calculating magnitude and things like that. So not anything you need to be concerned with for right now, I guess is what I'm trying to say. But glad you guys were paying attention and are curious to learn more about it. The third question was, do vectors always have to start from the origin? As I sort of indicated when we were doing vector addition, and in our original discussion of arrays, you can think of vectors as not starting from the origin, but when we sort of write it in this form, for example, v equals 1, 2, it's implied that the vector is starting from the origin and that these components sort of defined our terminal points or give us the length of the sort of x and y coordinates. That being said, you can always translate a vector, and when we did vector addition, we actually did translate the vectors in order to add them. So no, vectors don't always have to necessarily start from the origin, but you have to give a sense of like what context you're trying to do that in. Some people also asked, I guess, a more notational question, because when I was talking about magnitude, I sort of wrote 2 bars. I don't know if I did, but maybe at some point I wrote with just 1 bar instead. In our case, we're using both of these to represent vector magnitude. If this interior component is a vector, this is sort of just a notational choice. If you read different textbooks, some people might just use single bars, other people's will use double bars. The main reason to use double bars is to make sure that people are aware you're talking about norm or magnitude, as opposed to with the single bar, people tend to think of like absolute value, right? If you have a negative number, you can take its absolute value, make it positive. So not much of a difference here. It's just a notational thing. 5, how are vectors significant in quantum computing? This is a really great question. And as I sort of hinted to in our very beginning, when I was first talking about vectors, I introduced the notion that a quantum state is actually a vector. And as we'll be in the next lecture, we'll be learning about matrices, which are actually sort of operators you can multiply by vectors to change their magnitude and orientation and things like that. And in its most basic form, a quantum circuit, quantum algorithm can be decomposed into these vectors and matrices. So vectors are really at the heart of everything we'll be doing sort of throughout the course. And as we'll see in the next section on complex numbers, it turns out that complex numbers, which we'll also be using all the time when we're working in quantum computing, are also to some extent vectors. And then the final question, does vector addition have to be between vectors of the same dimension? Yes, yes, yes. I did not emphasize this. We'll be talking a bit more in the next lesson, next week's lesson, about vector shape and things like that, where we'll make this more explicit. But yes, if you are performing vector addition, it has to be between vectors of the same dimension. So for example, if I was to define the vector v equals 1, 2, and the vector w equals 1, 2, 3, I couldn't add those using our current definition of vector addition, right? Because there's no components or correspond in V corresponding to this third component in W. And again, we'll make this more explicit in next week's lecture, but for now, just remember that the vectors do have to have the same number of dimensions in order to be added. So that's a great question. All right, and with that, we'll dive into our discussion on complex numbers. So I wanted to start off by sort of motivating why people started thinking about complex numbers. For those of you who have taken algebra, you've probably seen the quadratic equation beforehand. And one thing that you might have encountered in doing this is that when you are taking the square root in your quadratic equation, it works fine, right? If b squared is greater than 4ac and you get a positive number. But what happens if you get a square root of a negative number? From what we know, there's no number that multiplies by itself to give a negative number, right? If we have a positive number and multiply it by itself, it's positive. If we have a negative number and multiply itself by it, it's negative. So how could you multiply a number by itself to get a negative, which would be a square root of -1? And there's actually a famous mathematician, Jerome Cardone, who discovered complex numbers actually in this very similar setting. He was trying to solve cubic equations and came across this problem. And he basically just addressed it by introducing the notion of an imaginary number, which we will be going into the next slide. But he thought that they were completely useless when he first discovered them and totally dismissed them, which is why they actually got the name imaginary. So sort of moving on, this is how we define an imaginary number. We say that we define the imaginary unit, I. So I is equivalent to the square root of -1, which means that if we take I squared, we get back -1 itself. And in this slide, I wanted to work through some examples of just some basic operations with imaginary numbers. So imaginary numbers can have a coefficient, which we call the imaginary coefficient. So for example, we could say define bi, where b is a real number, so it's a scalar like you've all seen before. If we try and square that, we get b squared, I squared, which is equivalent to -b squared. And so if I was to do this with an example, for example, let b equals 3, then we could define an imaginary number 3i, and if we square that, right, we get -3 squared, which is just 9. One of the other properties of imaginary numbers, or I guess one other way we can also define imaginary numbers is we can say if we have the square root, actually, let's say we have some real number a, a real scalar. If we have a square root of -a, where a is any real number, this just becomes square root of AI. And so if we let, for example, a equals 2, then, or how about we make it a equals 4. So if we have the square root of -4, this just becomes 2i. And so this is sort of how you can, in general settings, get out imaginary numbers and relate them to their imaginary coefficients. I wanted to spend the next few minutes going through a fallacy that some of you might encounter if you're not careful in working with complex or with imaginary numbers. So let's say that we have square root of 36, right, which we know is just 6, and we try being fancy, right? And so we say that 36 is, instead of 6 times 6, it's actually -6 times -6. Then we might think, okay, this is just equivalent to the square root of -6 times the square root of -6, which then gives us I square root of 6, I square root of 6, which is then equal to I square root of 6 squared, I squared. And then since I squared, right, is equal to -1, this would then give us -36. So somehow we managed to work out that 36, or square root of 36, is equal to negative square root of 36, or 6 is equal to -6, which we know can't possibly be true. So what actually went wrong? What was the wrong step here? Well, I'll break it down in terms of just like general cases. It turns out that the main false step was here. But in general, it's not true that if you have -1 equal to I squared equal to square root of -1 times square root of -1, you cannot, very important, cannot say that this is then equal to square root of -1 times -1, because then you would just get that it's equal to square root of 1, which is just 1. So this is a very important thing to keep in mind when you're working with imaginary numbers, and in general have to be a bit careful about it. And so I guess this was all very high level, and even though Jerome, he called them imaginary numbers, he thought they were useless. It turns out that imaginary numbers are actually super useful and used all the time, not only in quantum computing, but in engineering in general. And in today's lecture, we won't have time to like go into all those fun applications, but we're going to spend the next few slides sort of learning about imaginary numbers and more generally complex numbers and the different operations we can perform on them, so that you guys get comfortable just with the math, so that in later lectures we can begin to see why exactly these numbers are actually useful in applied settings. So now I wanted to, we saw what an imaginary number was, right? It's just the imaginary unit I multiplied by some imaginary coefficient b, which is a real number that we multiply by I to make it imaginary. Now, if we want to define a complex number, essentially all we're doing is we're adding a purely real number to our imaginary number. And because this A does not have an I associated, we can't just go and combine it with the B. These are two independent things, and it's actually written out in this form. So a complex number Z is equivalent to A plus IB. And so some numerical examples of this would be, for example, 3 plus 2I, 4 plus 3I, 7 minus 9I, etc. And we can, to some extent, consider any real number. For example, if we had the number 5, we could treat it as a complex number by just saying it's 5 plus 0i. So that's a real number. And any imaginary number, we could, to some extent, consider a complex number by saying it's just 0 plus 6i, for example. So those are some things to keep in mind. And with that, I wanted to throw a quantum quiz at you guys. And this should be pretty quick. Just go through and say whether the following numbers are complex and whether they're purely real or purely imaginary. So kind of disregard my last statement about how you can say that if it's real, you like add 0 times I. We're considering just purely real or just purely imaginary. I'll give you guys a couple minutes. The first 4 should be fairly simple if you were following along, but the last 4 might require a bit of manipulation on your end. All right, we'll move on to solutions. If you didn't get a chance to finish, you can come back to it later, but I'll quickly run through these. So the first one is a complex number because we see it has both a real and imaginary component. In 2, we see that there's no imaginary component, so it's purely real. For the third one, it only has an imaginary unit multiplied by its coefficient, so it's purely imaginary. And 4 was kind of just being a bit tricky with notation, but also purely imaginary. So question 5 was a bit more tricky because there is an I in it, but remember that I squared is actually equal to -1. So it turns out that this is actually just a real number. For number 6, although there is no I written, remember that square root of -1 is actually the imaginary unit. So it turns out that this is a complex number because we have a real and imaginary component to it. So for problem 7, again, it's a bit tricky. You might be a bit confused by having I cubed, but just remember your exponentials. We can divide this into I squared multiplied by I. This I squared then becomes -1. So we just get -11 times I, which is purely imaginary. And then our final example is just another easy one. So it's 1 minus I, which is complex. It has both a real and imaginary component. And with that, we'll now move on to this very cool notion that complex numbers can actually be represented as vectors in what we call the 2D complex plane. So what exactly makes a plane complex? Well, the complex plane, instead of having like the standard x and y axes, the x and y axes have very specific meanings. So in a typical Cartesian plane, we have x and y. In the complex plane, our x-axis is our real axis, whereas our y-axis is our imaginary axis. So what this allows us to do is if we have a complex number, we can treat it as a vector in which we put our real component in the x spot and our imaginary component in the y spot. And then when we go to plot it, what would have been our x component is just the sort of real coefficient of our complex number. And what would have been the y component is the imaginary coefficient in our complex number. And this is a really powerful interpretation. We'll see specifically why with Euler's formula in a few slides, but for now we can just think of it as allowing us to utilize the same manipulations as we can with vectors. And sort of to see why it's so powerful, we'll start by going through all of the algebraic properties of complex numbers in non-vector form, and then move into working with them in the vector form so you can see why it's so powerful. But for now, let's just go through an example where we define a complex number and then we plot it in the complex plane. So in our example, let's define the complex number z is equal to, for example, 3 plus 4i. So if we want to put this in vector format, we'll take our real coefficient and we'll set that to be our x component. And then we'll take our imaginary coefficient and set that to be our y component. So if we go to plot that on the real imaginary plane, our x component is 3, y component is 4, and our complex vector just looks like that. So this is just a direct application of exactly what we were working on in the first part of lecture. So now, how do we go about actually adding complex numbers? Well, sort of similar to vector addition, right? We added together the x components and the y components. In this case, we're going to add together the real coefficients and the imaginary coefficients. So as you can see here, in the general case, we have a plus ib, and then we're adding that to the other complex number c plus id. And so we added the real coefficients and the imaginary ones. So let's quickly work through an example. So we can define some complex number k equals -1 plus 2i, and some other complex number l equals 3 plus 4i. And so if we go about adding k plus l, that's equal to 3 minus 1, the real components, plus I times 2 plus 4. So that's equal to 2 plus. And another way we can go about it then is also thinking about it with our vector representation, right? So we'll create the vector k equals -1, 2, and l, vector l, equals 3, 4. We can then add together these two vectors, and we'll get -1 plus 3, 2 plus 4, that's equal to 6. Which then, if we put back in the complex format, is exactly the same as what we derived the other way. And so sort of similar to when we were doing straight vector addition before, you can actually go through and sort of plot out everything in the complex real plane. I'll go through it really quickly. So we have our vector k, which is -1, -1, 2. And we have our vector l, which is going to be adding 3 and then adding 4. Oops, it's a bit too big. And so we'll see that our resultant vector is actually this 2, 6 that we calculated before. So this is k plus l. So it's always good to check your work and make sure you're doing it both algebraically and geometrically, at least when you're first starting off. So hopefully the relationship between complex numbers and vectors is apparent in this case of addition. Next, we'll be walking through complex number multiplication. And so here you have to actually do some distributive property for those of you who took algebra in the American system, I remember we would call it FOIL, I think. So I'll quickly derive out where this equation comes from, just so you all are clear. So let's start with A plus IB times C plus ID. We have to go through and actually individually multiply out each of these components. So what this will give us is AC plus IAD plus IBC plus I square BD. And so then what we can do is AC stays the same. We can pull out both of these i's. We'll get AD plus BC. And then remember, again, I squared is equal to -1. So we can then combine these two real components. So we'll get AC minus BD plus I times AD plus BC, which is equivalent to the expression we have here. So that's just a quick derivation from where this formula comes from. In general, multiplying out complex numbers in this form is a bit annoying. So in a few slides, we'll be learning about a different representation, which makes multiplying complex numbers a lot easier. That being said, I wanted to just quickly work through an example of complex number multiplication. Just so you guys can get some practice, feel free to follow along with me since it's fairly similar to what you've been seeing before. So let's say k is equal 1 plus 2i, and L is equal to, I don't know, 3 minus I. Okay, so k times L, that's 1 plus 2i times 3 minus I. And remember, we have to FOIL it out. So that'll give us 3 minus I plus 6i minus 2i squared. And so remember, I squared is -1, so that cancels out with the negative here and it becomes positive. So we get 3 plus 2 plus I times 6 minus 1, which gives us 5 plus 5i. And we could go through and I guess plot each of these vectors. So the resultant vector would be at 5, 5, whereas k looked like 1, 2, and L looked like 3 minus 1. So I guess the reason for plotting it was kind of just to show in this case that complex number multiplication doesn't have a very nice relationship in the geometric plane, right? Before we could say like if we're doing vector addition, we just translate one of the vectors, we add them, and we get the resultant vector. But in this case, there isn't as nice of a relationship, right? Because we actually have these cross terms. And this is because in actual, in vectors, there's not this similar notion of vector multiplication. So geometrically, it doesn't have as nice of an appeal as complex number addition. So moving on, I just wanted to give you guys some time to do some practice with complex number multiplication and addition. I'll give you a minute or so.
Also, Fran, we are coming up on time, so just wanted to see how much longer you needed.
Yeah, I would say it's probably roughly 10 to 15 minutes more.
Okay.
So if people can stay on the call an extra 15 minutes, that's great. Otherwise, I think we'll be posting this recording. So you can also watch the concluding part of this lecture if you have to go.
Awesome. Thank you, Fran.
No worries. And so with that, since we're running short on time, I won't spend sort of too much time going through these derivations. You can check your work on your own. These first two problems are fairly straightforward applications of what we just learned. This third problem, though, is actually hinting at sort of the next idea that we'll be discussing, which is complex conjugation. So in complex conjugation, you essentially negate the value of the imaginary component. So in this case, it's plus, whereas in this case, it's minus. And it turns out that if you multiply a complex number by its complex conjugate, you end up getting a real valued number, which is equivalent to the sum of the squares of the coefficients. That was a lot to say, and we'll have a slide on that soon. Actually, right now. So I guess this was prefacing that. So complex conjugation, it has a variety of notations depending on what field you're in. So in this case, I wrote it as A plus IB with this bar over it. So if we have some complex number Z, we put a bar over it, that's indicating a complex conjugate. You could also, in some cases, it's illustrated with a star, and there's other notations. So just keep that in mind. So if we want to go through a quick example of complex conjugation, let's say that Z is equal to 3 plus 4i, then the complex conjugate of 3 is simply 4 minus i. And alternatively, if we have some complex number W, which is equal to, I don't know, 2 minus 2i, then its complex conjugate is 2 plus 2i. And if we go and actually draw that out in the complex plane, Z is the vector 3, 4, whereas W is the vector 2, or actually I'll just write it out. So this is the vector Z, and its complex conjugate is simply just negating the imaginary component. So what that corresponds to is flipping about the real axis. So it goes from here to here. And we would see something similar with W. For the sake of time, I won't drop it out or draw it out. So given that we've defined the complex conjugate, we can also define this notion of a complex number modulus. So when we write out these sort of bars, like equivalent to the absolute value, or in the case of vector and norm, if we put that around an imaginary number, Z, which is equal to A plus IB, essentially what this is telling us to do is to take the square root of, we can write it out as square root of Z times Z conjugate, which is on the square root of A plus IB times the negation A minus IB. And then if we go and actually multiply that out, we get A squared minus IAB plus IAB minus I squared B squared. And we see that these imaginary parts cancel out. This I squared, right, is equal to -1. So this becomes positive. We can cancel that out. So essentially, we're just left with square root of A squared plus B squared, which is the equation you see up here. And this is a really, really important operation on complex numbers. It kind of is equivalent to finding the norm of a vector, right? It's the sum of the square of the components of the complex vector. And if we take the square of it, we just get rid of the square root. So with that, I wanted to just pull out a few problems, practice problems. I think for the sake of time, I'll let you guys sort of just go through these on your own following the lecture. I think, yeah, the key thing to emphasize here is that the complex modulus is just a complex number multiplied by its complex conjugate. And the reason why we multiply the complex number by its complex conjugate and not itself is to make sure that we are getting rid of those imaginary coefficients in the middle and just getting out a result which is the sum of squares of the coefficients, which then corresponds to the vector magnitude or norm. And so the last sort of key concept in today's lecture is Euler's formula and complex exponentials. And this was sort of what I was hinting at before when I told you that there was actually an easier way to go about multiplying complex numbers. The derivation for Euler's formula is a bit involved. It involves Taylor series and things like that. So we won't be going over it in the scope of this class. But for those of you who are comfortable with the unit circle, essentially, this boils down to thinking about our complex vectors instead of being in the Cartesian plane, actually thinking about them in the sort of polar coordinate system, where a vector is defined by a radius r and a direction, sort of phi or theta, whatever you want to call it. And in this case, specifically, we're setting our radius to be 1 in the diagram here. But more generally, any complex number can sort of be boiled down to this form, right, of we have our vector length z, we have some angle theta, right? And so the x component corresponds to multiplying z by cosine theta, and the y component corresponds to multiplying z by sine theta. And you should all be comfortable with this fact from your high school math review. And so what Euler's formula says is that if we have an imaginary number of this form, we can actually write it as an exponential, e to the power of I times phi, where phi is sort of how we parameterize our complex number. And so with that, I wanted to quickly work through an example, which is actually going to be a proof of Euler's identity. So using our equation from the previous slide, we know that e to the I pi plus 1 is equivalent to cosine of pi plus I sine pi plus 1. And we know that the sine of pi is 0 and the cosine of pi is -1. So this gives us -1 plus 1, which is then equal to 0. So that's Euler's identity. And in polar coordinates, we could sort of represent this as, since this is the complex number, which has radius 1 and theta equal to pi, pi is just giving us the vector here. And then this quantity 1, we could think of it, right, as 1 plus 0i, right? So 1 being our real component, 0 being our imaginary component. If we write that as a vector, we get the vector 1, 0. So if we draw that, we see that these two vectors, then if we were to add them up, we could bring this vector over here. We would see that it would take us back to the origin, giving us 0. So that's sort of a somewhat explanation of Euler's identity, which is pretty famous and was used in the introduction of Euler's formula. For the sake of time, I'm gonna skip over this history tangent, take a look at the slides if you're interested in learning more about some fun history regarding Euler's formula and Euler's identity. One of the key things I really wanted to emphasize with complex numbers are these two identities that are actually really important to know, and you might see coming up. They come up all the time in electrical engineering, especially, and they might come up on some homework problems. So I wanted to make sure I took some time in class to just go through the derivation for this first formula. I'll leave it up to you to prove this one. So for this first formula, and we can write this out, right, as cosine phi plus I sine theta, plus, and then this will be cosine negative phi plus I sine negative phi. All of this over 2. And what this is equal to then is cosine phi plus I sine phi. We know that the cosine of a negative number, or of a negative angle, is still positive, whereas for sine, it flips value, right? So we see that then these two cancel. We get 2 cosine phi over 2. The 2's cancel, and we get cosine phi. So that's a very quick proof of why this equation holds true, and I'd like to challenge all of you to go after lecture and prove this second equation regarding sine phi. And so sort of the last thing I wanted to emphasize with these complex exponential form, and the main reason why we use them, is that it makes multiplying complex numbers way, way simpler. So if you have a complex number of this form, e to the I phi, times a different complex number, e to the I theta, the multiplication is simply just the addition of the exponentials, right? We know our properties of exponential multiplication. So for example, I was going to work through a whole example where I multiplied two numbers in the standard Cartesian form and then multiplied two in these exponential form and showed that it's a lot less work. But for the sake of time, I'll just go through an example. So imagine that we have e to the I 2 pi times e to the I 3 pi over 2. If we multiply these out, that's e to the I pi over 2 plus e to the 3 pi over 2, which gives us e to the I 4 pi over 2, which is just e to the I 2 pi. And then if we want to be a bit fancy, we can write that out cosine 2 pi plus I sine 2 pi. And we know from our unit circle again, right, that this is just 1 plus 0i equal to 1. All right. And so, yeah, if we sort of go back and compare our different equations, right, we see that multiplying numbers out in the Cartesian form of these complex numbers is a lot more complicated than when we work in polar form. And it turns out that in quantum computing, more often than not, you'll have what we call complex phases that are very important, but very frequently have to be multiplied out. So more often than not, you'll be working in this form, actually, which will save you some work in the long run. And so sort of the very last thing to note, since these complex exponentials are sort of encoding vectors, we once again have the notion of modulus, or sort of vector length. And when we're working in this complex exponential form, it's actually very easy to calculate out. So e to the I phi has a magnitude of 1. So if you have a complex number with a vector length that has to be sort of greater than 1, you'll multiply it by some radius or vector length r, and that's simply the complex exponential modulus which falls out. So let's work through a quick example. Let's say you have z equals 3 to the ei 5 pi over 2. It can be whatever wacky angle you want. If you find the magnitude of this complex number z, this will just cancel out and you'll just be left with 3. And you can actually work through it if you'd like, right, using our previous form where we say this is 3e to the 5 pi over 2 times its complex conjugate, which is e 5 pi over 2. We know that the complex conjugate in the exponential form is just found by putting a negative sign in front. And so what you'll see happen is you'll have 3 times 3e to the 5 pi over 2 minus 5 pi over 2. These cancel out, become 0. So you're left with square root of 9e to the 0 square root of 9, and that is just 3. So that's sort of a more longhand definition of what's going on. But the simpler thing to remember is just if you have a modulus with a sort of complex phase, it'll cancel out. And so as I hinted to before, you have this notion of complex conjugation in this complex exponential form. It's really simple. It's just taking a negative sign and applying that to the exponential. So we can quickly see that by writing z equals r e to the I phi, which is equal to r cosine phi plus I sine phi. And if we want to take the complex conjugate of that, right, in this form here, that's equal to r cosine phi. We negate the sign in front of our sign. And then if we distribute that back into these phases, we get r times cosine of negative phi plus I sine negative phi, which then goes into re negative I phi. So all of this work to then see that we just introduce a negative sign. So again, working with the complex exponential is pretty simple as well in terms of conjugation. And these are some really good practice problems to go through. I know we were a bit rushed here towards the end, so I'll leave this for you guys to work on in your own time. And there will be solutions posted as well. Definitely go through. It's some good practice. And I wanted to just conclude the lecture by showing this fun comic from XKCD, which you will all understand now that you know what a vector is, what a complex number is, and that a complex number can be thought of as a vector. All right. Sorry for running a bit over. I'll pass it to Kira now to make some announcements.
Awesome. Just really quickly, Fran, are your notes going to be available for students with the annotation?
Yeah. I'll make sure to save a PDF and share it with Rachel so she can share it with all of you guys and you can work through the derivations. If there are any things that aren't clear or that I spoke but didn't write that you guys would all find useful, I'm happy to write more notes out.
Awesome. So yeah, just to reiterate, Fran will be sharing her lecture notes and what she's written out. So you will have access to that. Unless we say otherwise, that will happen going forward. Just to reconfirm, you know, this semester is largely building the foundational skills necessary for next semester to really delve into these subjects. as the weeks go on, we'll be making more comparisons and in your labs, how this relates to quantum computing. So you may not understand right now how vectors and scalars are connected, but they are. And so just hang tight a little bit. This foundational knowledge is extremely important. In terms of just a few announcements, I want to go over. One, please make sure you read all the announcements on Discord in course announcements. We've shared information about Canvas, daylight savings time change, which started today, homework FAQs, and more. In the course announcements section in Discord, this will always be where you can look for course information. Number two, time changes with the labs. So we did say that there would be a time change. We asked you to take that into consideration when you were making your lab. So there shouldn't really be any need to change, but if it's absolutely unworkable, your current lab time, then please email us. The deadline to fill out the Canvas troubleshooting form has passed more than 24 hours ago. You should have already tried to log on to Canvas. This is your final reminder to please follow the instructions we provided to log into Canvas and make sure that you submit your homework. Which brings me largely to my final point on the homework. The homework is due tonight at 11:59 p.m. Eastern time. We did extend the deadline. In the future, the homework will now be due at this time every week. So it's due now on Sunday nights, Eastern time, instead of Saturday nights. We took into account the feedback that all of the Saturday lab students had to offer and wanted some additional time. So that was based on your feedback. And then for those of you that are still struggling with the homework, every Friday we will be having homework review sessions, as well as student assistant office hours on Friday. All the information is on Discord, so you can look more for that as well. And last but not least, on the homework, I want to remind all of you that we are not expecting you to get perfect scores or even close to it on the homework. Don't quote me on this, but I believe some sort of the calculation is around, 30%. I think you need to get correct if you attend your lab sessions and complete the course evaluations that we ask you to fill out. So please do not, this is not like a lot of your high school courses where you can get 100%. We don't expect it. Please don't be stressed out. If you are really struggling with the homework and you've attended the homework review session, we're here to help and want to make sure that this is not a stressful experience. Just last thing, we posted about this in Discord, but for the pre-evaluation assessment that I had asked you all to do at the beginning. Obviously, we kind of broke Canvas. As all of you, thank you so much for jumping on Canvas so quickly. It should be up and working. We are going to likely reset the assessment because I know it timed out for a lot of you. So we'll post more information. You'll hear about this in your lab. Again, thank you all for another incredible lecture. Thank you, Fran, for the lecture, and we'll see you all in your labs this week. Thanks, guys.